Hey folks, in this video we're going to discuss rotational motion of a rigid body. Simply, a rigid body is defined as a collection of particles that are constrained so none move relative to each other. Now this should be ringing some bells because it's strikingly similar to the physical definition that we applied to a reference frame in Chapter 3. And that was a collection of at least three non-collinear points that are rigidly connected or rigidly attached, and then the distance between any of these 2 points in the collection can't change with time. And so you can see the difference here is only in the use of particles versus points, because if a rigid body has at least 3 points, that's the same definition of a reference frame. And so when we have a rigid body, we can simply attach a reference frame to that body, and we call that the body frame. And each body frame is developed using that operational definition of a reference frame in which we have 3 basis vectors that are fixed within that reference frame. Now what's nice about using this body frame is that the mathematics are identical to the polar frame, which we've discussed and we've done work with ad nauseum and used that repeatedly. And so the only difference, though, is between those frames is really subtle, and it's that a polar frame is always pointing to a point. It's to a particle. That's when we use the polar frame. And so we don't really need a rigid body at all. But then the body frame is always attached to a rigid body. We see this in the diagram below, in which we have the rigid body B, and we want to understand the kinematics in relation to the inertial reference frame. The inertial reference frame is defined in the same way we have before, in which we define a point O, which is fixed within the inertial reference frame, and then there are 3 basis vectors, E sub 1, E sub 2, and E sub 3, which then define our reference frame. Now take a look at the rigid body. There are 2 points that are fixed within the rigid body. We have an O prime, which is any arbitrary point on the rigid body, and then we also have the point P. We attach a reference frame B to the rigid body, which has a fixed point O prime as the origin of the reference frame, and then 3 basis vectors B1, B2, and then B3 that would be coming out of the page. Now with the points O prime and P have a position vector defined between them, and that position vector is r, p with respect to O prime. And because this is a rigid body, the position vector itself never changes length. So we say that the norm, r of p with respect to O prime, will be constant no matter what. And the last thing that we see on this diagram is that we have an angular velocity. And this is the angular velocity of the reference frame B, which is our body frame, as observed by the inertial reference frame. And so what's now new about a rigid body is that unlike particles, which can only translate, rigid bodies can both translate and they can rotate. And because they can translate and rotate now, that means that the velocity, or the inertial velocity of one point on the body, let's say O prime, won't necessarily be equal to the velocity of another point P on the same rigid body. So what we're saying is that different points on a rigid body can have different velocities depending on where they're observed from. So let's demonstrate that, and let's find an analytic expression for the velocity of point P as observed in an inertial reference frame. This P is fixed to the rigid body. And so to do that, we're first going to write our position vector of point P with respect to a point that's fixed within the inertial reference frame. So that would be our position vector r, P with respect to point O, and this is going to be a combination of the 2 vectors of the position vector O prime with respect to O, plus the position vector of P with respect to O prime. And so to find the velocity of P with respect to O as observed in the inertial reference frame, we simply need to take the time derivative as observed in the inertial reference frame of the 2 position vectors, so O prime with respect to O, and we'll add that to the derivative as observed in the inertial reference frame of the position vector P with respect to O prime. And so if we approach this in its 2 terms, we've seen this first term before. And this first term is the same as saying it's the velocity of O prime relative to point O as observed in the inertial reference frame. And we call that the translational velocity. And this will become apparent as we work through this problem. And then the second term, if we write that in terms of our velocity, it's the velocity of P with respect to O prime, okay, not point O, but with respect to O prime, as observed in the inertial reference frame. And we also call this the rotational component. And this rotational component is going to be directly related to the rotation of the rigid body itself. So that was omega of the body frame relative to or observed by the inertial reference frame, omega b with respect to I. And so it's really the second term that we need to do some work on. So let's take this, the velocity of p with respect to O prime as observed in the inertial reference frame. We said this is equal to the time derivative as observed in the inertial reference frame of r p with respect to O prime. Now because the points P and O prime are both fixed on the same rigid body, they have a fixed distance from each other, and we can write their coordinates in the basis that's fixed to the body. So we can write that in terms of a B1, B2, and B3 basis. And we'll use our Cartesian coordinates. So the vector we're writing is rp with respect to O prime, and that's equal to a distance x in the B1 direction plus a distance y in the B2 direction. We're only dealing with planar kinematics, so there isn't a B3 direction. We're all in the same plane, so it would be 0 in the B3 direction. And recall that we said that rp with respect to prime, the norm of this is constant. And so in our expression, we take the time derivative, as observed in the inertial reference frame, of x in the B1 direction plus y in the B2 direction. We use the chain rule to distribute the derivative throughout all the terms, and so that gives us the time derivative in the inertial reference frame of x multiplied times B1 plus x times the time derivative in the inertial reference frame of B1 plus the time derivative of y multiplied times B2 plus y times the time derivative of B2. Now, taking into consideration that the length of this vector never changes, that means that x and y are both constants. So if x and y are constants, then the time derivative of x is equal to 0, and the time derivative of y is equal to 0. But the time derivative of these basis vectors, as observed in the inertial reference frame, isn't 0. So we need to take the time derivative of those. So recall that the time derivative is simply the cross product of the angular velocity of that reference frame with the vector itself. So we'll pull down our x, and then we'll take the time derivative of b1 by the cross product of angular velocity of b with respect to I crossed with b1, and then plus y, it's angular velocity of b as observed in inertial reference frame, crossed with b2. We'll simplify this by pulling out our omega terms. So this is equal to omega of b as observed in the inertial reference frame, crossed with x multiplied times b1, or x in the b1 direction, plus y in the b2 direction. And we should recognize this component because it's simply our position vector of p with respect to O prime, and that's equal to x in the b1 direction plus y in the b2 direction. So we replace this, and so our velocity of p with respect to O prime, as observed in the inertial reference frame, is omega of reference frame b as observed in the inertial reference frame, crossed with our position vector of p with respect to O prime. These are 2 points that are fixed on the rigid body. And then that's our rotational component of our velocity. So now that this is all said and done, we have our velocity of point P as observed in the inertial reference frame is equal to two components, the velocity of O prime with respect to O as observed in the inertial reference frame, plus the rotational component, which is omega B as observed by the inertial reference frame, crossed with the position vector r of P with respect to O prime. And so it's a two-term velocity equation. And so what this tells us is that if we know the translational velocity of any point on a rigid body, which we'll just call O prime, and we know the rotation of that rigid body, the rotational velocity of that rigid body, as observed in an inertial reference frame, and then we know the position vector between the point that we're interested in, which is point P, relative to that point that we know the translational velocity, then we're able to calculate the velocity of point P as observed in the inertial reference frame.